Hey everyone, welcome to our final unit. All done after this. So this unit is about circular motion gravity. I think it's the coolest unit, so I hope you guys enjoy it. So let's get started. Circular velocity, or also known as tangential velocity. So when an object moves at a constant speed, what formula do we use? Well, we use V equals d over t, right? And if we were talking about the distance around a circle, what do we use? Well, we could use circumference is equal to 2 times pi times the radius, or pi d, but 2 pi r, same idea. And when we're talking about the time it takes to complete one circle, what do we use? Well, that's our period, or t, right? So what this means is that if we want to find the velocity of something moving in a circle, instead of distance, we're talking about our circumference, right? The time it takes to complete one circle. So we can use 2 pi r instead of our distance, and instead of time, we can call it period, because that's the time it takes to complete one circle. And what we have is we have a brand new, spanking new formula here, which is Vc equals 2 pi r, but really it's just d over t. Okay, so Vc is our tangential velocity, r is our radius, t is our period, and pi is pi, 3.141516 or whatever pi is. On your calculator, use the pi button. So it's assuming that it's moving at a constant speed as it travels around a circle. So this word tangential comes up, and the reason that it's called the tangential velocity is if I draw a tangent line in this circle, and a tangent line is just a straight line that only touches at one point. So that's our tangent line right there. So if this was moving in a circle and I sort of let it go, well, it would always fly off at a tangent, right? If I let it go right here, it would fly off at a tangent. If I let it go, right here, it would fly off at a tangent like that. So that's why it's called a tangential velocity, because that's the direction that it always is. It flies off at a tangent. So let's do a question. A 30-centimeter vinyl record revolves around a turntable and turns the record around at 33 1/3 rotations, or revolutions per minute. Calculate the speed the needle at the start of the record playing at the outside edge of the revolving record. Okay, so they give us the diameter of the record, and they give us 33 revolutions per minute. And when we ever have per minute, it means that this is a frequency, right? So if we want to answer this question, we can use our new formula, Vc equals 2 pi r all over t. And you can find this formula because it's talking about speed. It's found under the speed part of our formula. So this is down here under speed, distance, time, and acceleration. So 2 pi r divided by t. So we already know 2, we know pi. And we know our radius is 15 centimeters because the diameter was 30 centimeters, so it's going to be 15 centimeters, or 15 meters, 0.15 meters here, so that's 15 centimeters. And then we just need to find our period. So it's set at 33 1/3 revolutions per minute. So to get a period, we need that time to be on top, and we also probably want this to be in seconds. So I'm going to turn my minutes into seconds, because I know there's 60 seconds in 1 minute. So now we have revolutions per second. And if I want seconds to do 1 revolution, if I want to flip it, I just have to 1 over all of this. So what I would do here is I would go 33.33333333, put in a whole bunch of threes because it's 1/3, and then divide it by 60. Oops. And then I would just 1 over that, and I get my period to be 1.8 seconds. So the 1.8 seconds would go here, and now we are ready to answer this question. So we just have to go 2 pi times 0.15, and then divided by 1.8. And we find the speed of it is, we have 2 sig digs, so 0.52 meters per second. Okay, and that's how we'd find our tangential velocity. That's how we'd find our speed. So speeds at different parts of the circle. So in this question, it said on the outside edge of the revolving record. So it actually makes a difference where you are in the circle depending on, where you are in the circle for what speed you're going. So 2 people are standing on a giant record player. Which person is moving faster, person A or person B? And you're thinking, well, here's the center of the record. They're on the same record, so shouldn't they be moving at the same speed? Not exactly. That's not how it works with circles. So if we look at our formula, VC equals 2 pi r, the time it takes B to get from here to here and the time it takes A to get from here to here has to be the same, right? A and B will always be lined up in the record, so they will always get to the same spot at the same time. So this period has to be the same for all of them. What changes is that, well, the radius is different, right? The distance that A travels to get from here to here and the distance that B travels to get from here to here is very different, right? And that's because, well, their radiuses are different. So if this is the radius of B and this is the radius of A, let's say that A has twice the radius of B. So we double this here, 2 pi stays the same. So the only thing that we're changing on this side is we're doubling the top. So then our speed must be double. So A, if it's double the radius out, it's traveling twice as fast as B. And that's important, you need to know that. So when you move further out in a circle, you travel a longer distance, so you have to move faster. So the further you out are in a circle, the faster you're moving. And you might have felt this. So if you're spinning in a circle, if you've been on like a tire swing as a kid and you're spinning in a circle and you let your neck go out, it sort of like snaps back and you can feel that extra speed. So another thing we need to talk about is circular acceleration, or what we call centripetal acceleration. So what's the definition of acceleration? So the definition of acceleration is how fast we change our velocity. So it's our change in velocity in a certain amount of time, right? And remember that acceleration is a vector, and that's important. So it's our change in velocity over time. So can you accelerate without changing your speed? Lots of people would think, no. Well, no is the correct answer. You can't accelerate without changing your speed. But what about if we talk about velocity? How is velocity different than speed? So velocity is a vector, and speed is scalar. Right? So velocity has a direction, and speed does not. So can you accelerate without changing your speed? Well, we have to look at this in terms of velocity. So let's say I'm moving in a circle. So say this is a traffic circle, the Sherwood Park traffic circle by the school, and we're moving at a constant speed and we just move around. So here, I'm going 5 meters per second. And then as I'm traveling here, remember our velocity is always at a tangent. I'm going 5 meters per second. And then here, I'm going 5 meters per second. And here, I'm going 5 meters per second. So my speed is not changing, right? I'm going at a constant speed. But if we think about it in terms of velocity, well, this is 5 meters per second south. This is 5 meters per second east. This is 5 meters per second north. This is 5 meters per second west. So is my speed changing? Well, no. Is my velocity changing? Yes, because velocity has that direction aspect to it. And the acceleration is our change in velocity over time. So if we're changing our velocity, then we are accelerating. So can you accelerate without changing your speed? Yes, by moving in a circle. Your speed stays the same, but because your direction is continually changing, you are technically accelerating. Okay. So centripetal acceleration is a special type of acceleration where your speed does not change, only your direction. So the only way to do this is to move in a circle or some portion of a circle. So we have two formulas for determining centripetal acceleration. And these are different because we're moving in a circle. We have AC equals v squared over r, and AC equals 4 pi squared all over t squared, where AC is our centripetal acceleration, v is our tangential velocity, r is our radius, t is our period, and pi is, well, pi, right? And all these are is if you take Vc equals 2 pi r over t, what you're doing is you're saying that, okay, we have this r down here, and then we're going 2 pi r divided by t, and all of this is squared because our velocity is squared. So this would become 4 pi squared r squared all over t squared divided by r. These would cancel out. So this formula over here is just a combination of this one and a combination of this one. They merge them together for that. Okay, so you can use either one to find your acceleration. So a car turns a curve with a speed of 20 meters per second. If the radius of the curve is 100 meters, calculate the centripetal acceleration. So how do I know which formula to use? Well, let's write them both out. So we have AC equals v squared over r, and we have AC equals 4 pi squared r all over t squared. This one is a much nicer one to use, but you can only use it if they give you a speed or you're trying to find a speed. If they don't give you a speed or you're not trying to find a speed, you're forced to use this one. And you can find both of these on the data booklet. They're just right there on the data booklet, so that's where you can find them. Okay. And because they give us the speed, we're going to use this one. So we want to find the centripetal acceleration, so we just go 20 meters per second, and we square it, divided by the radius of the turn, which is 100 meters. And if we do that, 20 squared divided by 100, we get 4 meters per second squared. And we have 2 sig dig, so 4.0 meters per second squared. And if we wanted to make this a vector, make it correct, well, what's happening here, if I draw a picture, so the car is going around the circle, the radius of the curve is 100 meters, so we need a direction as well. So yeah, I'm going to hold off on direction, and I'll add that in a second. So 2 people are standing on a giant record player. Which person is accelerating more, and by how much more? So same sort of question as the first one, but I want to talk about it in terms of acceleration. So pause the video and see if you can figure out who is accelerating more and by how much more. And I will explain it right now. Okay, so we can use our formulas. And we can use this one. I should have left a little bit more space, but I didn't. I'm just going to switch my color. So this one's actually the easier one to use because A is twice the radius out. Right? That's the only thing that changes. The 4 doesn't change, the pi squared doesn't change, the period's the same for the both of them. So this says that the acceleration should be double. Right? If we use this one, it's a little bit more complicated. Right? The radius is doubled for A. But you have to remember, the radius is the velocity is also doubled, and because the velocity is squared, we have to square that as well. So 2 squared is 4. 2 on the bottom is 2, which is 2. So both say that the acceleration is double for A. Because it has a bigger radius, it's going to have double the acceleration, but this one's just a little bit easier to use. So it should be 2 times the acceleration for A. Okay, another board question. The Earth takes 365.25 days to complete one rotation. The Earth is 150 million kilometers away from the Sun. Determine the tangential velocity of the Earth. So pause the video, give it a go, and see if you can get this question. And I will go through it right now. So if it's asking for the tangential velocity, then we're going to use this one. And so they give us the Earth is 150 million kilometers away from the sun. Okay, so we can do that. 2 pi and 150 million kilometers. Cool. And then it says it takes 365.25 days to complete one rotation. So the period is 365.25. So I want I want it to be in kilometers an hour. If I'm going to do it, it's going to be in kilometers an hour. So 365.25 days. We want to turn days into hours. There's 24 hours in one day. Like that. Oops, that's backwards. 24 hours in one day. And that's all we have to do. So if I was plugging this into my calculator, it would be 2 pi times 150 million divided by 365.25 times 24. And my answer would be 107, or we have 3 sig digs, so 1.08 times 10 to the 5 kilometers per hour. Right? You could do it in meters per second as well. That'd be a little bit different, but you could do it. It would just be another conversion, or you convert this. Not a difficult conversion. Cool. So that's how fast we're moving right now. So that's actually crazy fast. That's like faster than any jet plane that you've ever been on. So why, ask yourself this, why are we not like flying backwards? Why aren't we like on a spinning ride where we're being sucked to the outside wall? Why doesn't that happen? Well, it has to do with, it doesn't matter if you're moving fast, it matters if you're accelerating. So the second part of this question, I ask you, find the acceleration of the Earth as it orbits the sun. So this is the key. Its acceleration determines the forces on us, not velocity. So pause the video and see if you can find the acceleration. So if I'm finding the acceleration, I can just use v squared over r. But if I'm doing acceleration, I can't be in kilometers an hour. So I'll have to take my last answer, and I'd use the full answer. And there's 1,000 meters in 1 kilometer, and there's 3,600 seconds in 1 hour, like that. So I'll have to make that conversion first. So I have to times my answer by 1,000 and divide by 3,600. And then I get my answer in meters per second. So now I can just plug it in, right? I can plug in my answer squared, I forgot what that was. And then I have to make sure that my radius is in meters. So I have 150 million kilometers. But if I want it to be in meters, I just have to add on 3 zeros. It just makes it into that. So if I take my answer in meters per second, and I square it, and then I divide it by 150, 1, 2, 3, 4, 5, 6, 7, 8, 9, we get that. That's our acceleration. So we have an acceleration of 0.00595 meters per second squared. So that's nothing. That's like such a small acceleration. That's, if you were accelerating like that you wouldn't feel it, right? We feel 9.81, and if we go 9.81 divided by that, that's how much bigger gravity is, almost more than 1,600 times bigger. So the reason that we don't feel that we're moving that fast is because our acceleration is so small. So that's key. Okay. Centripetal force. So circular force or centripetal force. According to Newton's first law, objects will continue in a straight line at a constant velocity if no net forces are acting on the objects. Does this apply? Well, no. If we're moving in a circle, we're not moving in a straight line, so this does not apply. So Newton's first law doesn't apply to this question. Newton's second law says when a net force acts on an object, it will accelerate. Does this apply? Well, yeah, we're accelerating, right? We said that if we're changing our direction, we're accelerating. Does this apply? Yes. So we use physics principle number 1, not physics principle number 0. That's the idea. So which direction would the net force have to push to make it move like this, to make it move in a circle? Well, if I push this way, right, all that would happen is my object would accelerate in a straight line that way. If I push that way, well, my object's going to go out like that. And if I push that way, well, my object's just going to slow down in a straight line. So the only way that I can push it in order to make it go in the circular direction is towards the center, right? My F net has to be towards the center. And as it switches direction, I have to switch my force in order to make it always go towards the center. So my net force always goes towards the center, of the circle. That is key. Okay. So we're going to sum up these directions, and we're going to add a direction to acceleration. So my velocity, let's switch up my colors. My velocity always goes off at a tangent. So that's, sorry, this is confusing because my mouse jumps around like that. Let me fix that. Okay. So my velocity always goes off at a tangent, right? If my object is here, my velocity is going off at a tangent. If my velocity is here, my object's going off at a tangent. And if it's here, my velocity is going off at a tangent. In order to make it move in that direction, my force has to be, my net force has to be towards the center of the circle, right? And if it's here, it's towards the center of the circle. Here it's towards the center of the circle. Here it's towards the center of the circle. So my net force always has to be towards the center of the circle. So we never gave a direction with acceleration, but if my, right, remember that F net is equal to ma. Force is a vector, acceleration is a vector, but mass doesn't have any direction. So that means that my acceleration and my force have to be in the same direction. So my acceleration is also towards the center of the circle as well. Okay. So acceleration and force are towards the center of the circle. Velocity is always at a tangent. And if I go back to that example that we did over here, calculate the centripetal acceleration of your car, the direction would be towards the center. So we need a formula for centripetal force. So to find centripetal force, we use F net equals ma. We don't use the term F net for things moving in a circle. What we use is we use the term FC. FC and F net are the same thing. It's just special when it's moving in a circle. So instead of saying F net, we use FC. Instead of saying A, we use AC. So to get the formula for centripetal force, all you have to do is add an m to both sides. So what that means is that, well, we know that AC is equal to V. Oh, let me give myself a little bit more space. V squared over r, right? That's acceleration. And if I want to turn it into a force, right, I add an m to it. But if I add an m to this side, I have to add an m to this side. So this is the formula that we get. So Fc is equal to mv squared over r. Okay. Same with the other formula. So I also know that AC is equal to 4 pi squared r all over t squared. Well, if I want to make it a force, I need to multiply it by mass, and then it becomes that. So I'd have to multiply this by mass as well, and that becomes our formula. And you can find these formulas on your data book, and because it's a force, it's under forces. So you can find it on the bottom right there, those two formulas. So centripetal force, we use that term centripetal force, is just a net force for circle. So different forces acting on an object can cause a net force or a centripetal force. So centripetal forces can be caused by a number of things. So they can be caused by gravity, they can be caused by friction, or they can be caused by tension in a string. And these are all the ones that we're going to analyze in Physics 20. In Physics 30, we talk about electric and magnetic forces, so electromagnetic forces, and we use all these skills. So that's why it's really important that you do this stuff now so you'll be good for Physics 30. So this is our last physics principle of Physics 20. We use physics principle number 2 here, and that's when things are moving in a circle. So that's when we use that FC equation. Okay, so let's do an example. A 60-kilogram child is being whirled on a merry-go-round. The radius of the merry-go-round is 6 meters. If there's a coefficient of friction between the 60-kilogram child and the ride is 0.6, so everything's like 6, what would be the maximum speed you spun your child? Okay. So first thing you have to do this question is we have our child. This is a top view. This is my child, and it's being spun around on the merry-go-round. So what's keeping that child on there? Well, if he's just sitting here, it's this force of friction that keeps that child on the merry-go-round, right? So what's causing my net force is my force of friction. That's the main force that's acting on it. And we don't include gravity because we'll talk about gravity tomorrow. If this is a top view, so this is you looking overhead. This is a side view. We want to focus on the things that make it move in a circle. So this is the center of the circle right here. Gravity is going downwards, and gravity doesn't help it move in a circle. So friction is the only thing that makes it move in a circle. So we can break this down. And because they give us we're trying to find a speed, we can use mv squared over r. And our force of friction is the same one as before. That's mu Fn. Right? If this is our force of gravity and it's a level merry-go-round, then Fg is going to equal Fn. So we can break this down further. So we can have mv squared over r is good, and mu is good. But force normal is going to equal my force of gravity, and force of gravity is equal to mg like we did before. My masses cancel out. I can move r up there like that and square root it. So we end up getting v is equal to my coefficient of friction times g times r. So my coefficient of friction in the question is 0.60. G is 9.81 meters per second squared. And my radius of my merry-go-round is 6 meters. I square root that, and I can find out what the maximum speed is. I don't like doing square root first. So 0.6 times 9.81 times 6. And then I'll square root that. So the speed of my child at 2 sig digs is 5.9 meters per second. So the next question asks, well, what would happen if you spun the child faster than that? Well, when we do this, when we look at this formula here, what we're saying is that, well, what are the requirements to make it move in a circle? What does the force of friction provide to help make it move in a circle? And then we look at these ones. So we have mu mg like that. G is a fixed amount. It's 9.81. The mass of the kid is going to stay the same, and the coefficient of friction is going to stay the same. So all of this can stay the same. But on this side of the equation here, if we increase our speed, well, this number would get bigger while this is staying the same. So what that means is that if the speed gets bigger, well, the requirements to make it move in a circle become bigger than the force of friction can provide. So as long as you're under this speed, you're good. But if you get bigger than that speed, well, all of a sudden, yeah, your force requirements become too big. And whenever you leave the circle, you fly off at a tangent. So I have a video here that shows this idea. So we'll watch this video. So they're just using a scooter to make it spin around really fast. They're being safe with helmets. But you can see as that speed increases, the force on their neck gets bigger and their heads start to snap back. Their legs are flying out. So they flew off at a tangent, right? When the speed becomes too big, you fly off at a tangent, and he doesn't die, I don't think. I don't know. He looks okay. He looks fine. Just missing a shoe. So yeah, and this wasn't even just force of friction holding them down. This was a force applied by the bar. So yeah, the faster you go, the bigger your force requirements are. And if you don't have those force requirements, then you spin off at a tangent. Okay, so we're almost done here. A common misconception with moving in a circle is the feeling that we get when we're traveling in a circle. So the kids on this feel like they're being sucked outwards. And what a lot of people think is they think because they're getting sucked outwards that the force is outwards. So that's a common misconception, is they mistake the feelings with forces. So we feel like we're being sucked outwards, and this is just due to inertia, right? If you're traveling if you're traveling in a circle here, right? Your body wants to fly off at a tangent. And what's required is this back wall here needs to create a force inwards. But since you want to continue moving in a straight line, you're going to feel like you're being sucked outwards because that wall is sort of keeping you in. So I have another video here. Let's watch the video, and that'll sort of help explain this. And this is a gravitron ride, and gravitron works with this idea of inertia. Inertia, I don't know if I've talked about inertia before, but inertia is just Newton's first law. Inertia is a resistance to change in motion, and inertia, it just means that you want to continue traveling in a straight line. So what's happening with these people is they feel like they're being sucked outwards to the wall, but what's happening is they want to continue on the straight line, and as they try to continue on that straight line, the back wall here is providing a force that is not allowing them to do that. So that force is pushing on their back, and it gives them a sensation of being sucked outwards. So what's important to remember is that although they're being sucked backwards, it's just inertia. The force is by the wall, and the force is this way. Just like my arrow here, the force keeps them going towards the center of the ride, keeps them traveling in that circle. Okay, so I have one last board question, so I'll let you do this board question, and yeah, so give it a go, pause the video, and I will go through it right now. So a 600 kilogram horse bites onto a rope and is swung in a horizontal circle at a constant velocity. The radius of the rotation is 1.2, and then the period is that. What is the tension in the rope? So we have a circle here. Here's our horse. It's being flown in a circle like that. So what keeps that horse going towards the center of the circle is that force of tension. So our force of tension, what makes that horse move in the circle, is our force of tension. We can break this down. So we don't have a speed, and we're not trying to find a speed. So we have to use that m4 pi squared r all over t squared formula, and that's going to equal ft. And that's all you have to do. So my mass is 600 kilograms times 4 pi squared. My radius is 1.2 meters, because the length of the rope as it's going in a circle is going to be your radius. So 1.2 meters, and then our period is 8 seconds, so we have to square that as well, and that's all we have to do. So we would just go 600 times 4 pi squared times 1.2 divided by 8 squared, and you get that as your force of tension. So your force of tension has to be 444 newtons to make it move in a circle like that. Okay, so these are your homework questions, so give them a go. And as always, if you have any trouble with them, let me know and I can help you out.